Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, for today's special problem, I have here a paper reminiscent of Lucas Kovar's famous paper on the band structure of germanium back from the early 2000s. This paper is titled Free Particle Motion on an Air Track My Butt. A preliminary report on an unexpected force, a suspicious clock, and my willingness to accept credit, by Jeff Bernard. Let me read the abstract to you. I attempted to verify the dullest result in introductory mechanics, that a free particle moves at constant velocity. The apparatus behaved impeccably, the data were clean, the conclusion was absurd. When position was plotted against the time recorded by a wind-up stopwatch recovered from a back closet, the motion appeared to exhibit a constant acceleration opposite the direction of travel. This report documents the observation, rules out obvious mundane explanations such as drag, and briefly entertains the possibility of new physics before reluctantly admitting that the clock is probably at fault. Check this crap out. So, the introduction rightfully points out that free particle motion is governed by a very simple kinematic equation, that x as a function of time, here I'm writing time tau, and you'll see why momentarily, is equal to the initial position plus the velocity times the time. Any deviation from linearity in x would ordinarily signal a force, pseudo-force, or possibly some new physics. The apparatus employed was a 10-meter air track with glider cart. I'll display in the video what a 10-meter glider air track looks like if you're unfamiliar with that. Anyone that's taken Physics 101 lab class has probably used one. It was carefully leveled and supplied with steady airflow. The glider floated freely and showed no visible tendency to drift, scrape, or wobble. Position data were extracted from a CCD camera triggered by a mechanical wind-up stopwatch discovered in the back closet next to a moldy sandwich and several items labeled "Do Not Use." Well, that's probably a bad sign. The stopwatch ticked audibly and confidently, which at the time I took as a positive sign. Results. Figure 1 shows the cart position plotted against the stopwatch time tau. Similar to the paper, I've reproduced the data up here. The data are remarkably consistent across multiple runs. A quadratic fit of the form, well, here I've given us a quadratic fit. It's in the purple line here, and I've written the equation that approximates that quadratic fit. Not exactly, but approximates. Matches the data extremely well, as you can see. The purple line seems to track the points of data taken. For comparison, I also fit the data to the straight line form required for free particle motion. That fit is included as a dashed line. It's a red line here on the board, right here. This fit is included. It is visibly poor. I included it anyways to demonstrate that I did at least briefly consider the possibility that nothing interesting was happening. The next section is titled Why It Is Probably Not Drag, Unfortunately. The most obvious explanations for the observed curvature is friction or drag. However, several observations argue against this. First, the air track appeared visually fine, airflow was steady, the glider floated cleanly, and no contact with the track was observed. Second, standard linear drag would produce an exponential relaxation in velocity when expressed in a trustworthy laboratory time, not the clean quadratic dependence seen here when plotted against tau. Third, repeating the experiment with different initial speeds produced the same apparent acceleration, which is not what one expects from ordinary drag effects. The next section is titled Speculation, because why not? If the cart is truly free and the data are taken at face value, then one is forced to contemplate less conventional explanations. A previously unknown weak force acting only on air track gliders cannot be ruled out on the basis of this experiment alone, although it would be oddly selective. A relativistic explanation is also tempting in the abstract, though the cart speed was far below any regime in which special relativity is known to become interesting. I mention this only to demonstrate intellectual bravery. That said, I would be perfectly happy to accept credit for discovering new physics if such credit were offered. However, I am increasingly suspicious of the clock used here, as its ticking became uneven and slightly alarming. Finally, the conclusion of the paper. The cart moved freely, the data were clean, the straight line fit was terrible, the quadratic fit was beautiful. Whether this indicates a profound discovery or merely a bad clock remains to be seen. For now, I conclude only that a free particle accelerates if you let your clock lie to you. And that is exactly the point here. And so, what's the problem aspect of it? So let me lay out the theory, and then I'll give you the opportunity to pause the video if you want, come back to it later if you've worked on the problem a bit, and see if you can fix the data here. So let me first say that when you encounter a fictitious force of some kind, your first suspicion should be in the time. If that checks out, then next you should check the space. So in that case, you're looking for some kind of non-inertial reference frame. So although this is kind of a fake problem, it can be tied back to a real-world problem that was dealt with back in, I think, the 1929, but I'm not 100% on that year, in which the position of the moon as tracked from Earth was called into question. It's had an anomalous acceleration that they could not explain. So either Newton's laws were wrong, and this is, by the way, not a general relativity. It's not something that general relativity fixed outright. And in the end, they adopted this kind of dynamical system of time. So this dynamical system of time, you could call it ephemeris time, based on what are called ephemerides, which is the plural of ephemeris, which is derived from the Latin word for diary. So it's basically a book. And an ephemeris is essentially a table of times and positions for a planet or the moon or a comet or an asteroid or something like that. But again, this idea of dynamical time. So what we do is we assume that the way that we measured the time was bad. For example, if we were basing it on the revolution of the revolutions of the Earth, called sidereal time, which is non-uniform, which gives rise to the problems I think that they had with the moon data, then you correct it by assuming Newton's laws work just fine, and so you create this kind of tabulated time. And that's what you use to predict the positions of things like moons and planets and whatnot. So that is what you should do in this problem here, is create your own ephemeris, so to speak. And I will lay out the theory behind it before giving you the opportunity to proceed and kind of decode this data and generate a new table of values where we have a good clock and its position. That would be the ephemeris itself. So I use tau here for the bad clock, this suspicious clock, this wind-up clock that the author mentioned in the paper. And so let's unpack that now. So let's assume that our data, in terms of its positions that were measured, were taken in terms of this bad clock, which is actually a function of a good clock. So now we have this kind of bad clock time dependence, rather than just simply being an independent variable. So we've parameterized it. The velocity then, as a function of a good clock, would now you just simply take the derivative of this. So take the time derivative of x as a function of tau, which is a function of t, the good clock. And here we'll just apply the chain rule. And so we'll see that we're going to get dx d tau times d tau dt. So that's just a straightforward application of the chain rule. Now what I want to do is I want to pull out this pseudo-force, if you will, which we're going to do by drawing out the acceleration. So we can calculate the acceleration from this. So this would be the second derivative of x taken with the bad clock. So taking a second derivative will give us the acceleration as given by a good clock. And this time we have to employ the product rule. So we'll do the time derivative with respect to the good clock of dx d tau times d tau dt. And doing so, and simplifying a little bit, we'll get d tau dt squared times d2x dt squared, d tau squared, plus dx d tau times the second derivative of tau with respect to t. So solving for this pseudo acceleration, d2 d tau squared, we get that that's equal to minus dx d tau times d tau dt squared divided by d tau over dt squared. And of course, the pseudo-force itself would be the mass times this, so I could simply multiply through times the mass. And this would be the pseudo-acceleration, or from the pseudo-force that we are seeing here, the one that he describes as in the opposite direction of the motion. So this is our fictitious force. So with that bit of background, now you have the opportunity to solve this problem of resolving the bad clock and showing how it gives rise to the pseudo-force that we see here. So you can pause, come back later after you've had a chance to try it, then resume and I'll show you the solution. So from the fit, we see that we have x of tau is equal to x naught plus v naught times tau minus 1/2 a times tau squared. So here in the data, as I indicated, it looks like the v naught is 1 and the acceleration component is 1/10. That's from the fit. But free particle motion, which is what's going on as we know, x of t, which would be what we would get from a good clock, should be equal to x naught plus v naught times t. This is what we should observe. Consistency, however, requires that x of tau be equal to x of t. And from this, dx dt should be equal to dx dt, dx d tau dt. But dx d tau is equal to v naught minus a times tau. So v naught minus a times tau times d tau dt is equal to v, which implies dt d tau is equal to v naught minus a tau divided by v. So we can now integrate this to arrive at an equation for t in terms of tau, which is going to give us 1 over v times v naught tau minus a over 2 tau squared. But what about this v? So we have to make an assumption here. We'll assume that the clock is correct at t equals 0. And so doing that, this means that d tau dt at t equals 0 is equal to 1. Then we will get 1 is equal to v naught minus a tau, which goes to 0, divided by v, which means that v naught is equal to v. So replacing v with v naught, we get that t as a function of tau is equal to tau minus a over 2 v naught times tau squared. So using the values that we got from our fit, this would be tau minus 1 over 20 tau squared. And so now we can use this formula here to construct a table, or ephemeris, of position and time data where the time is taken from this dynamical consideration. So, using this formula to calculate the true time, given a value for tau, notice that each of these entries, the x component, here it was 0. Again, we assume that it agreed at t equals 0, so 0, 0 goes to 0, 0. But thereafter, you'll notice that the time entries are changing. So instead of being 1, 1, we get 0.951. And the next entry would be 2, 1.7. Well, the x position is the same, 1.7. But now the time entry, instead of being 2, is 1.8. And you can see how these trace all the way down. And if we were to graph this, of course, I'll just draw a little mini graph here, we would get data points that lined up into a nice line fit, as we knew it should. Yeah, and I think that's probably all there is to say about this. Again, when dealing with issues like this, the thing you should blame first when you have these fictitious forces show up in data is the time, and then next you should blame space, i.e. non-inertial reference frames. So kind of a corollary problem to this would be, instead of the time being the problem, the bad clock that didn't keep good time, if instead you were to use a system, maybe doing some kind of air track experiment, maybe in a rotating drum or something like that, where you're going to get a centrifugal force component that you'd have to pull out. And though this was a fake problem, again, this does have real-world applications. It's been done, the use of this kind of dynamical time to fix the trajectories of celestial bodies has been done since the 1920s on, because our natural clocks that we used to use in the past are just not very good. Whether you're tracking, the rotation around the sun or the rotation of the Earth, something like that, these are just not good clocks. Now, of course, we use atomic clocks, but it is what it is. So that's it for this special problem. If you have any ideas for special problems that might be fun to try to tackle, you can post that into the comment section, or you can find the email to this channel in the channel page. Send me an email. Well, I'll see you next time.